Hello everyone, welcome to this video on determining whether a set forms a basis for a vector space. So in this video, I'm going to start off by defining something that I've defined in videos past. What does it mean for a set of vectors from a vector space to be a basis for that vector space? And then after that, I have several pages where pardon me, where I give examples of very commonly used bases for some very common vector spaces called standard bases. Then I talk about the definition of the dimension of a vector space and give examples of that. And finally, the heart of the video, the title of the video. In the last part of the video, I'm going to be going over examples on where I'm giving a set of vectors from a vector space, and I'm asked to determine whether or not this set of vectors is a basis for that vector space. Okay. So first page here, just definition of what does it mean for a set of vectors to be a basis for a vector space. Alright, so a set of vectors, say S equals this set of n vectors here, v1, v2, to vn. All these vectors are from a vector space called V. A set of vectors from a vector space is a basis for that vector space if the two following things are true, if the two following statements hold. One, the set S is what they call linearly independent. Alright, so that meant that each vector in S cannot be written as a linear combination of the other vectors in S. A way to check that for independence is looking at this equation, where if you were to take a linear combination of the vectors in S, a1 times v1 plus a2 times v2 plus all the way up to an times vn, where a1, a2, an, right, those are all scalars. Set that equal to when is that equal to the 0 vector, and try to find solutions, find these values of a1, a2, an, right, a3, whatever, that make this true. If this equation has only the trivial solution, right, meaning where a1, a2, a3, all the scalars are 0, if it has only that trivial solution, then the set of vectors is linearly independent. You cannot write any of the vectors in the set as a linear combination of the other vectors in the set. And at the same, also this is true. S has to span the vector space V, right? S spans V. And again, what this means is this, that every vector in the vector space, right, I'll call it every vector V from, lowercase v from vector space V, can be expressed as a linear combination of the vectors in S. So that means if I took a vector, vector little v here, I should be able to write vector v this way as a linear, a1 v1 plus a2 v2 plus an, plus an vn for some scalars a1 through an. I should be able to take any vector in the vector space and write it as a linear combination of the vectors from S. Alright, so if both of these things are true, both of them hold, then they say that S is a basis for V. Now another way you could think of a basis, a set of vectors that's a basis, is that these vectors are like the building blocks for V, for the vector space. If I can build the entire vector space by just using these n vectors, because every vector in the vector space is a combination of them, and I need all of them because they're independent, right? I can't just get rid of one because, if they were dependent, that means one of them could be written as a linear combination of others, and that means I wouldn't need that one, right? So you could, again, I like to think of these as building blocks for the vector space. You know, I can build out every vector from the vector space by taking linear combinations of these, and they're all necessary because they're independent. All right, I need all of them to be able to build the entire space. All right. So now I've got here on the next few pages some examples of what are called standard bases. So a commonly used basis for a vector space is called a standard basis for that vector space. I'll tell you this right now. Bases are not unique. A vector space can have multiple different bases, all right? But very often there's a standard one, right? A one that's very easy to use, very easy to build off of, right? Like I was saying on the previous page, think of these as building blocks. You know, the standard basis is like the simplest basis, the one with the simplest building blocks for that vector space. So some examples here. Now you've probably seen these in other videos of mine. The set with just the vector 1, you know, these are vectors from R2, right? Vectors with two components, 1 and 0, 0 and 1. Or you could also say this was from the set of 2 by 1 matrices, right? But I'll just think of these as vectors from R2 right now. With 1, 0, 0, 1, this is the standard basis for R2. Again, it's not the only basis for R2. There are others out there, plenty. But it's the standard basis because it's, again, it's like the simplest building blocks. You know, every vector in R2 is some linear combination of these two vectors, and these two vectors are linearly independent. They are not, you know, scalar multiples of one another, right? That's all you need to check for when you only have two vectors. When you're checking for independence, you know, are they scalar multiples or not? 2, you know, second example, 1, 0, 0, 0, 1, 0, 0, 0, 1. These are vectors from R3. These three vectors form a basis for R3. These are the standard basis for R3. These are like the simplest building blocks for vector space R3. Right? Every vector in R3 can be written as a linear combination of these, very simply. And these three vectors are linearly independent. You cannot write one as a linear combination of the other two. And you might notice something from these bases for Euclidean space, you know, R2, R3, R4. Every one of these vectors is basically just a column from the 3 by, you know, these are the 3 columns from the 3 by 3 identity matrix. You know, these are the columns from the 2 by 2 identity matrix. If you remember what those look like, you know, it's just 1s down the main diagonal and 0s everywhere else. So in general, right, for n-dimensional Euclidean space, Rn, the standard basis is all the vectors. I called these vectors vi, such that vi is the ith column of the n by n identity matrix, right? So vector v1 would be the first column. Like this would be v1, v2, and v3 if I was talking about R3. And this would be v1 and v2 if I was talking about R2. All right, so like the vector I is the ith column of the n by n identity matrix, and that would have what, n vectors in it, right? Because there are n columns in the n by n identity matrix, just like there are 3 columns here when R3, 2 in R2, right? But, you know, so you're probably familiar with these, right? R2, R3, Rn, Euclidean spaces. But those aren't the only vector spaces, and I put up a video before about other types of vector spaces. I've got some of those here, right? Some standard bases for other kinds of vector spaces, right? So again, it's just the simplest building blocks for these spaces. So like here the vectors aren't, you know, just vectors with components, they're polynomials. So the set with 1 and x, right? These two vectors, right? These two polynomials in this time. This is the standard basis for this P1. Remember the P with a subscript, this fancy P with a subscript? represents the set of all polynomials of that degree or less, so degree 1 or less. And think about that, right? Any polynomial of degree 1 looks like something times x plus some constant, which would be something times 1, scalar times 1. So every polynomial, every vector in P1 is a linear combination of these two. And, there's only two vectors here. They're not scalar multiples of one another. I can't multiply this by a real number to get x. I can't multiply x by some real number to get 1. They're linearly independent. So that's, again, they're the simplest building blocks for P1 standard basis. And then it's very similar to this for P2, P3, P4, and so on. Number 5 here, the set with 1, x, and x squared is the standard basis for P2, which is the set of all polynomials that are degree 2 or less. Right, something times x squared plus something times x plus something times 1. Right? Every vector in here is a linear combination of these three, and these three are independent, right? Because I can't write one as a linear combination of the other two. So in general, for these p with a subscript sets, these fancy p's, these sets of polynomials, for p, the standard basis, right, the set with the simplest building blocks for Pn, the set of all polynomials of degree n or less, is 1, x, x squared, x cubed, right, all the way up to x to the nth power. That would be again, the simplest building blocks for that set, that vector space. Then you have, after these sets of polynomials, I have also introduced you in other videos to sets of matrices, right? Vector spaces of matrices with real entries. So this R 2 by 2, right? This is the set of all 2 by 2 matrices with real entries. That's a vector space. And the simplest building blocks, right? The standard basis for R 2 by 2 is all these 2 by 2 matrices where you have exactly one entry that's equal to 1, and then the other entries are 0. So one in the upper left-hand corner for this matrix, and then one in the upper right-hand corner. And basically I fill in each position with a 1 at some point in these vectors, and all the other entries are zeros. So I got 4 vectors here, 4 matrices from this set. And every matrix in this R 2 by 2 is a linear combination of these 4. And these 4 are independent, right? And again, you can check that on your own, but that means that each vector in here, each matrix, cannot be written as a linear combination of the other 3. They are independent. And this is very similar, right? This next one is sets of matrices with real entries. This is for R 2 by 3. So you see there are, in a 2 by 3 matrix, there are 6 positions, 2 times 3, right? So I have 6 matrices here where there's a 1 in one position and 0 everywhere else, right? 1 here, 0 everywhere else, 1 here, 0 everywhere else, 1 here, 0 everywhere else, etc. So again, this set of 6 vectors, again, these are the simplest 6 vectors that make a basis for R2, the standard basis for R2 by 3. So in general, all right, for R m by n, right, the set of m column and n row matrices, m row and column. It's rows by columns, I apologize. So the set of all m by n matrices with real entries has a standard basis where you have all the matrices that are m by n, where exactly one entry is equal to 1 and all other entries are equal to 0. So just like this in the previous example with the 2 by 2s. And how many would be in here? Well, if you have an m by n matrix, that means there are m times n entries to fill in, right? So there'll be m times n elements in here, m times n vectors, whatever. They see 2 by 3 ones, there were 6 vectors, right? Remember in the 2 by 2, 2 times 2, there are 4 vectors in the basis. Okay. And of course there are others out there, plenty of other examples of vector spaces and standard bases for those vector spaces. But I just went over some basic ones, some types of vector spaces I've introduced in other videos, right? These sets of polynomials of degree n or less, these sets of m by n matrices with real entries, and of course Euclidean space, right? R2, R3, R4, Rn. Right? Okay. So now that we have a idea as to what a basis is, right? What you need to show to show that a set is a basis for a vector space, that it's independent and that it spans the space. We've seen some examples of some standard bases for some special vector spaces. Now I'm going to go into defining the dimension of a vector space, and again, this is something I've brought up in past videos. If you've been following along, if not, here it is again. The dimension of a vector space V, denoted by this as dim of V, right, dimension of V, is the number of vectors in a basis of V, right, really any basis of V. Now I say a basis because, again, the bases for a vector space are not unique, right? Those standard bases I was showing you before on the previous pages, those are not the only bases of those vector spaces. But what you're going to notice is that every basis of a vector space is going to have the same number of vectors in it, and that number of vectors is going to be called the dimension, right? The dimension of the vector space. So looking at those previous 9 examples of standard bases, we now know the dimensions then of some vector spaces. So from those examples earlier, right, the dimension of R2, right, the two-dimensional Euclidean space was 2, right? I called it two-dimensional Euclidean space before I said what the dimension was. It's 2, because there were those 2 vectors, right, 0, 1, and 1, 0, in the standard basis for R2. So any basis for R2 is going to have 2 vectors in it. The dimension of R3, right, that standard basis had 3 vectors in it, so the dimension is 3. Right? And any basis for R3 is going to have 3 vectors in it. And I put in boxes like some general statements. The dimension of just any Euclidean space, Rn, the set of vectors with n components, is n. Right? And any basis for Rn will have n vectors in it. Then for those sets of polynomials of degree 1 or less, or degree 2 or less, or so on, remember that P1 earlier in the video. The standard basis had the vectors 1 and x. So the standard basis had 2 vectors in it. Alright, so the dimension of P1 is 2. The dimension of P, and again, any basis for P1 will have 2 vectors in it, 2 polynomials. The standard basis we saw earlier for P2 was, consisted of 1x and x squared. That's 3 vectors, right? 3 polynomials. The dimension of P2 then is 3. And any basis for P2 will have 3 vectors in it. And so on, right? And the dimension of Pn, right, that had 1, the standard basis had 1, x squared, all the way up to x to the nth. That's n plus 1 vectors in that basis. So the dimension of Pn is n plus 1, right? So the dimension of P4 would be 5, the dimension of P7 would be 8, etc. Alright, and then for the sets of matrices with real entries, the vector space of 2 by 2 matrices, remember that standard basis had 4 vectors in it, right? So the dimension of the 2 by 2 matrices vector space is 4. You saw earlier the 2 by 3 matrix vector space had a standard basis with 6 vectors in it. And again, it's just the product of rows by columns, really. Right? So the dimension of our 2 by 3 is 2 times 3 is 6. And every basis of that space will have 6 vectors in it, 6 matrices. And the dimension of the, just the set of n by n matrices is m times n. Again, just rows times columns. That's how many matrices, that's how many vectors will make up any basis for that vector space. And again, dot, dot, dot here, and so on, right? You could find other examples of vector spaces out there. Do a quick search online. Usually these Euclidean in a lot of introductory linear algebra texts I've seen, the basic ones that you're introduced to are the Euclidean spaces, these sets of polynomials and sets of matrices. Again, there are sets of, there are vector spaces out there that have infinitely many dimensions, right? These are all considered finite dimensional vector spaces because there's only so many vectors in each basis, 2 and 3 and 6. It stops at some point. But in a previous video I put up, I talked about vector spaces of continuous functions. Functions that are continuous over the real number line, or functions that are continuous over a certain closed interval on the real number line. Those vector spaces would be infinitely dimensional, have bases that have infinitely many vectors in them. But for the purposes of this video, we're not going to be talking about infinitely dimensional vector spaces, even though I have mentioned examples of them here and in videos prior. But for the most part, we're going to stick with finitely dimensional vector spaces. All right. And now there is a nice relationship between basis and dimension that I'd like to talk about here. Bases and dimensions of vector spaces. And that's this here. Now I don't have a proof for this. We can develop a proof if you'd like. Send me a message. But this is just a nice relationship. If this is something nice that if you know what the dimension of a vector space is beforehand, and you're given a set of vectors, very often you'll be able to quickly decide whether or not this set of vectors forms a basis for the vector space or not. So suppose S is a set of k vectors, right? So v1, v2, all the way up to vk, right, where k is some whole number. Be a set of k vectors from a vector space V that has dimension of n. Meaning, the dimension of V is n. So, that means any basis for V will have n vectors in it. Now, 1. If k is less than n, right, meaning that the number of vectors in this set is smaller than the dimension, so the number of vectors in this set is less than the number of vectors that would be in a basis for V, well then S can't be a basis, right? And the reason for that is S would not span the vector space. All right, if the number of vectors in the set that I'm given is less than the dimension of the vector space, then the set will not span that vector space. There will be some vectors in the vector space that cannot be written as a linear combination of these k vectors. And you can figure that out and find that on your own for whatever examples we're looking at. That's case 1. 2. If the number of vectors, if k is greater than n, right, so the number of vectors in this set is larger than the dimension of the vector space. So the number of vectors in this set is greater than the number of vectors in a basis for V. Well, then the set is going to be linearly dependent. right? Not independent like we like, right? That means S won't be a basis, because remember, a basis for this vector space is going to have n vectors. And if we have more than n vectors, then S can't be a basis. And the reason for that is S would be linearly dependent. Right, so that means one of the vectors in the set S could be written as a linear combination of other vectors in the set S. So some of those vectors would not be needed. We'd have to shrink it down so that it had n vectors to have a basis for V. Whereas in case 1, we'd have to extend it. We'd have to add vectors to get a basis for V. All right. So if the number of vectors is smaller than the dimension, S doesn't span V, it's not a basis. If the number of vectors is larger than the dimension, then you're going to know that S is linearly dependent. It can't be a basis for V. Now, what if it's equal to the number of the dimension? What if k is equal to n? So the number of vectors in S is the same as the number of vectors that would be in a basis. Now that doesn't mean you have a basis. Right? You still have to determine whether or not the set is a basis, but you're closer to it though. You can't just immediately say, like in cases 1 and 2, you can't immediately say it's not a basis. Well, if k equals n, then the following statements are equivalent, right? Meaning they'll have the same meaning. So A, S is a basis for V, B, S spans V, and C, S is linearly independent. So if the number of vectors in S, sorry, pull that back down. So if this is the same number of vectors as in a basis, right? If there are n of these vectors, what that means is that we just need to show one of these to show all three of these are true. Right? That's what it means for the statements to be equivalent. You just need to show that one of these is true for all three to be true. So I've put that down in words here. Right. So this means that when the number of vectors in the set S is equal to the dimension of the vector space, in order to show that S is a basis for V, you either show that S spans V, or you could show that S is linearly independent. Right. Again, this is only if you know the dimension. Right. If you don't know the dimension of the vector space, then you have to show both. You have to show that S spans the vector space and S is linearly independent. All right. But if you do know the dimension, if you know the dimension of the vector space, then you only need to show one of these things, because the other one will follow. All right. The other one would be an equivalent statement according to this thing I wrote up here. All right. So if I know the dimension, then I only need to show that S is either spanning V or S is linearly independent. And then as a personal preference, I prefer just showing independence. Because, when you show that a set spans another set, or if you're showing that a set is independent, you're pretty much setting up a similar system of equations. You'll see this all boils down to solving a system of linear equations. And so the reason I like having, with the same coefficient matrix, so the reason I like just testing for independence, because I know the other side is just going to be the zero vector instead of just some generic vector from V, so I don't have to worry about writing, V1, V2, V3, V4, whatever the components of the generic vector from V are. I can just write zeros on the other side because I'm testing for independence. Right. But again, when you know the dimension, you only need to show one of those things, spanning or independence. But if you don't, all right, one more time, sorry. If you don't know the dimension of the vector space, you have to show both. Right? You have to show that the set spans the vector space, and you have to show the set is linearly independent. Okay. Now, the reason I showed this to you is because, I went over some examples earlier of, dimensions of certain special vector spaces that we know of. Right, Euclidean spaces, those sets of polynomials, sets of matrices. And the examples I'm going to get into now are going to be dealing with those vector spaces. So these are going to be, we're going to have some vector spaces that we actually know the dimension of. So then to show that a set is a basis for that vector space, I only need to show that that set is linearly independent, or that it spans the set, spans the vector space. Right, but just one or the other and not both. All right, so my first example that I'm going to work out here for you. And this set of instructions up here is going to be the same for the rest of the video. All right, I am going to be determining whether the set of vectors S is a basis for vector space V. Now, I have done this in other videos, in a video in the past with Euclidean spaces, R2, R3, R4, etc. So I am not going to be doing those in this video. All right. I'm going to be working with other vector spaces, the sets of polynomials, the matrices, and so on. Really just those two, though. And we'll go from there. All right. So we're determining, is S... Now here, my vector space is that P3. All right. This is the set of all polynomials of degree 3 or less. And I'm asked to determine, is this set of... You see, the vectors here are polynomials of degree 3 or less, right? So 1 minus 2x squared plus x cubed, that's, that's vector 1. Right? That polynomial, comma. Negative 4 plus x squared is another polynomial of degree 3 or less, so that's another vector here, vector 2. 2x plus x cubed is another polynomial of degree 3 or less, right? Thus another vector, right? In this example, vector 3. And then 5x is another polynomial of degree 3 or less, right? So it's another vector, v4. So I have a set of 4 vectors, 4 polynomials, and again I'm asked, is S a basis for P3? Could I use these as building blocks for P3? Make every vector in P3 by just taking linear combinations of these, and are these independent? All right, so again, the reason I mentioned the result on the last page was, suppose now I'll make that note here. If you didn't know, if you didn't know the dimension of P3, then you would have to show both that S spans P3. Then you would have to show both that S spans P3 and S is linearly independent. I'll just say independent here. Okay, which is what I did in a previous video when I was doing this with the Euclidean spaces. I didn't, it was before I defined dimensions, so I didn't know the dimension of those Euclidean spaces, so I had to show both the spanning and the independence of the set. But we do know the dimension of P3 based on the standard bases earlier. Right? Remember, the dimension of P3 would have to be 4. Remember, the dimension of that Pn was n plus 1. All right. So since I know this, we do know that the dimension, so we only need to show one of those things. Right. We only need to show either, S spans P3 or S is independent. That's why I said that's what the last page meant. Okay. Now look at the number of vectors in S. There are 4 vectors in S. Now that's not less than 4. That's not greater than 4. All right, the number of vectors in S is equal to 4. So this is where we actually have to check, right? Because if there were only 3 vectors in here, I'd say it's not a basis, right? Because it wouldn't span P3. And if there were 5 vectors in S, then I'd say it wasn't a basis, because I'd know that because that's greater than the dimension, that set would be dependent, not independent. But there are 4 vectors in S. That's the same as the dimension, so I must check. All right. So what again? Like I said earlier, I personally, of the two, and they're very, very similar, checking for both. Does one span the vector space, or are they independent? I'm just going to check for independence. All right. And I'll be doing this for each one. All right. Check for independence. All right. So that's, remember, where we're looking at this equation. Where I take a linear combination, some scalar a1 times the first vector plus some scalar a2 times the second vector plus some scalar a3 times the third vector plus some scalar a4 times the fourth vector. And I'm saying, when is that equal to the 0 vector? All right. So again, this equation translates to a1 times, and then the first vector is this polynomial here, right? That's 1 minus 2x squared plus x cubed, plus, and then a2 times the next vector, which is this polynomial here, right? Negative 4 plus x squared plus a3 times the third vector, this 2x plus x cubed, plus a4 times the fourth vector is just 5x. And when is this equal to the 0 vector? All right, now in the set of polynomials of degree 3 or less, the 0 vector is the 0 polynomial. Is just I could write it like this if I wanted: 0 plus 0x plus 0x squared plus 0x cubed. Right, but again, that's just 0, right? But this is this is what every polynomial in P3 looks like, right? A constant plus a constant times x plus a scalar times x plus a scalar times x squared plus a scalar times x cubed. Right, I'm just writing it in the same form that every polynomial in P3 would look like, but that's just 0, right? All right, and then let's do what we do, the way scalar multiplication and vector addition are typically defined for polynomials, the way you normally add and multiply polynomials by numbers. I'm just going to kind of skip ahead to the end here, not the end of the statement, but put all the constants together. I'd have a1 times 1, right, so a1, then minus 4a2. I'm just looking at the constants, the one without x, with no x on it. And there's no constant in this polynomial, so nothing there, and then there's no constant in that one. So there's the constant term of the polynomial on the left side, plus, and then I'll combine all the first degree terms, or x to the firsts. Right now there's no x to the firsts here, no x to the firsts here. There'd be, if I distribute the a3, there'd be 2a3 x to the first, and then plus 5a4 x to the first. So these would combine times x to the first, plus, and then the coefficients of a to the second, or I'm sorry, x to the second. This first one I'd have negative 2a1, and then there's an x to the second here, so plus a2. There's no x to the second here, no x to the second there, so that's it for the x to the second terms. And then finally the x cubed terms. There's a1x cubed, right, so there's a1 there, and then no x cubed. There's an x cubed plus a3x cubed, and there's no x cubed in the last term. So a1 plus a3 would be the coefficient of x cubed. And this is equal to, again, you can write it as this, but I'm just going to put 0. Now, if you remember back from maybe algebra class, or intermediate algebra, or beginning algebra, or pre-calc even, the only time a polynomial is going to be equal to the 0 polynomial, right, which is the 0 vector here, all the coefficients have to be 0. So do you see what I said this earlier? You know, when you go to determine if a set spans a vector space, or when you go to determine if a set is linearly independent, you'll end up solving a system of linear equations with the unknowns. And the unknowns here are these scalars. Right? I'm trying to find a1, a2, a3, and a4 so that I get the 0 vector. And seeing if, you know, only the trivial solution is the solution to this, or if there are others. So this leads me to a system of linear equations involving the unknowns, involving the a1 through a4. Right? In order for this to be true, this polynomial to be equal to 0, I need a1 minus 4a2 to be equal to 0. Right? I need this coefficient to be equal to 0, 2a3 plus 5a4. I need that to be equal to 0. I need this coefficient to be 0, negative 2a1 plus a2 to be equal to 0. And the last coefficient, a1 plus a3, and I'm trying to line up the like terms here, a1s and a2s and a3s and a4s, equal to 0. You see the linear system? So no matter what vectors you have, you know, whether the vectors are, you know, from Euclidean space, or the vectors are polynomials, when you're trying to test for spanning or independence, you're going to end up solving a system of linear equations. Right, and then I'll write the corresponding, you know, augmented matrix here, and then we'll put that matrix. I'm going to go to the calculator, and you know, you can do it by hand if you want, but I'll go to the calculator. I'm going to put this in its, you know, you have the augmented matrix for this, which down the first column, the coefficients of a1, so 1, then 0, then negative 2, then 1. And then down the second column, the coefficients of a2, negative 4, 0, 1, 0. Coefficients of a3, 0, 2, 0, and 1. Coefficients of a4, 0, 5, 0, 0. And then, you know, there'd be a bar and zeros on the other side, but again, like just when you're checking for if a set spans a vector space, when you're checking for independence here, these systems that get set up will have the same coefficient matrix. So I'm really only going to focus on the coefficient matrix and just, you know, imagine I know that there are zeros on the other side here. Okay. Then I'll have this be put into reduced echelon form, or that reduced row echelon form. Right, so I'm going to go to the calculator here. Right, again, you can do it by hand. It might not take that long because there's a lot of zeros in this matrix, but I'm going to go to my 84 plus here, and again 83 is very similar. Go to the matrix menu, over to edit, and make a 4 by 4 matrix. That's what this coefficient matrix is. And down the first row, 1, negative 4, 0, 0, and then 0, 0, 2, 5, and negative 2, 1, 0, 0, 1, 0, 1, 0. Okay. Then I get out of here. Hopefully I've entered everything correctly, and then back to the matrix menu, and I want to put it in that reduced echelon form, or reduced row echelon form, RREF, in the math area under the matrix. And then go back to the matrix, enter matrix A, and here we go. And look, that's the identity matrix, right? The 4 by 4 identity matrix. Oops, sorry, 1 there, 0 there. Remember, there'd be zeros on the other side, so remember what this implies. implies that A1 equals 0 would have to be 0, A2 would have to be 0, A3 would have to be 0, and A4 would have to be 0. So only the trivial solution is a solution to this equation I set up in the beginning. The only way a linear combination of these vectors from S, the only way a linear combination of these vectors from S is equal to the 0 vector is if all the scalars, A1 through A4, if all those scalars are 0. So that tells me that the set S is linearly independent. Wonderful. All right, and like I said before, since I know the dimension of the dimension of P3 is 4, and there are 4 vectors in this set, I only need to show this or the spanning. Well, this is equivalent to the spanning. This actually implies the spanning. But yeah, you just need to show one of those two if you have the same number of vectors as the dimension, which this does. So this tells me that S is a basis for P3. All right, so every vector in P3, right, every polynomial of degree 3 or less can be written as a linear combination of these 4, and none of these 4 are linear combinations of the other 3. Right? They're independent. So these 4 you could think of as building. You could use those as building blocks to create, to construct the vector space P3, build that space up. Okay. One other thing I wanted to point out. Remember how, in the previous video, when I took a set of vectors from Euclidean space, written as like column vectors, and then I made I was testing for independence or testing to see if it spanned the vector space, and we created this system of equations, and it had this, they both had the same coefficient matrix, like, there's a coefficient matrix here. Remember how each column of the coefficient matrix was just one of the vectors from set S? Well, that's not the case here. I mean, this column is not 1 minus 2x squared plus x cubed, but look at the column though. Look at the column and then look at the coefficients of this vector. You have 1, 1, then 0, 0x, then negative 2, negative 2x squared, then 1, 1x cubed. So like down the first column were the coefficients of the first vector. And down the second column, negative 4, negative 4, 0, 0, 0x, 1, 1x squared, 0, 0x cubed. Down the second column were the coefficients of the second vector. And down the third column are the coefficients of the third vector. Down the fourth column are the coefficients of the fourth vector. So in a very similar fashion to what happened with Euclidean space when I was checking for independence or spanning and creating this coefficient matrix. Sure, the columns of the coefficient matrix aren't the vectors themselves, right, because they're not polynomials, but they do contain information about that vector. The first column, again, each column has the coefficients of the corresponding vector from S. All right, so I'm going to use that fact to speed up the next example. All right. So my next example is another one of these where my vector space is one of those set of polynomials of degree 2 or less this time. All right, so the vector space is P2, and I'm asking the same question, right? Is S a basis for P2? Right. Now, like I said in the last problem, if you don't know the dimension of P2, then you have to go and check for both. Does S span P2, and is S a set of linearly independent vectors? But we know that the dimension of P2 is 3. And look, there are 3 vectors. Right? Vector 1 is this negative 3 plus 6x. Vector 2 is this 3x squared. And vector 3 is this 1 minus 2x minus x squared. All my vectors here are polynomials of degree 2 or less. So the number of vectors in the set is the same as the dimension. So if that's the case, now it doesn't mean it's a basis. Okay? It doesn't mean it's a basis. I know the last example it ended up working out, but it means we have to check. All right? If the number of vectors is smaller, you don't have to do anything. It's not a basis. If the number of vectors is larger, you don't have to do anything. It's not a basis, not independent. But if the number of vectors is equal, again, we have to check either one or the other. Does S span P2, or is S linearly independent and they're equivalent to each other in this case where the number of vectors in S is equal to the dimension? All right. So again, I'm going to check for independence. I'm looking at this equation, A1 times V1 plus A2 times V2 plus A3 times V3. When's that equal to the 0 vector? Now, again, the 0 vector here would be 0 plus 0x plus 0x squared, or just 0. Now, I'm going to skip ahead to the coefficient matrix. All right. The matrix for the system that you'd be solving. Remember last time down the first column were the coefficients, starting with the constant term, the way I had it set up. I had it set up so the constant terms were first. You could reverse the order, go highest powered first if you want. But I'm going to set it up with the constant first. So down the first column, I have the coefficients in ascending order of the first vector. So there was negative 3 for the constant term, then positive 6 for the x to the first term, and then 0x squared. And then down the second column, the coefficients, again starting from the constant term and going in ascending order, the coefficients of the second vector. There's 0 for the constant, there's 0x to the first, and there's positive 3x squared. Alright, and then for the third column in the coefficient matrix, the coefficients, and again starting from the constant going in ascending order, the coefficients of the third vector, 1 for the constant, negative 2 for the x to the first, and negative 1 for the x squared. And again, you'd have a bar here and then some zeros if you were testing for independence. If you were checking for spanning, you'd have like v1, v2, v3 over here for the just representing some general vector or the coefficients of a general vector in P2. All right, and then I'd like to put this into reduced echelon form or reduced row echelon form. And again, this one really isn't so bad to do by hand, but I just want to save a little writing and go back to this here, and I'll enter the matrix. Right, it's a 3 by 3. You can do, and first row, negative 3, 0, 1, 6, 0, negative 2, 0, 3, negative 1. Alright, and then the last thing I entered was reduced row echelon form, so I'm just going to re-enter that by going second entry. And you can change this to fractions you want under the math menu, change to frac, but I know what those are, right, as fractions. So we have here, 1, 0, 0, 0, 1, 0, and it looks like negative 1/3, negative 1/3, and 0 again. So you see this row of zeros, but when we're talking about independent, the row of zeros tells me that S doesn't span. I mean, you could check either way. This row of zeros tells me S does not span P2, right? Because there'd be infinitely many solutions to this, and oh, actually, The only way this, if you were looking at any vector, sorry, if you were looking at any vector from P2 and have like V1, V2, V3 over here on this side, there'd be some combination, there'd be some vector out there such that this entry here was not 0, and then you'd have no solution to the system. So there'd be some vectors out there that couldn't be written as a linear combination of these three. So 1s does not span P2, so already we know it's not a basis. But then another way to tell is looking at the pivot columns, right? Not every column is a pivot column in the coefficient matrix, right? Not every column is a pivot column, right? With those leading ones, in the reduced echelon form here. So that tells me that S is not independent, right? S is dependent. And you can tell too, right, if these were zeros, like when you're testing for independence, right, there's zeros over here. The bottom row, like you have a free variable, so there'd be infinitely many solutions to this equation. You could replace A1, A2, and A3 with lots of different things and get all sorts of non-trivial solutions. So again, from that also you can say that S is dependent. So either way I'm looking at this, right, either way I look at the coefficient matrix in reduced echelon form, reduced row echelon form, I'm seeing that S, right, from either one of these, I'm seeing that S is not a basis for P2. All right, and then if you'd like too, right, I mean we could also see that S is not a basis. All right, so sorry, fumbling my words. So like the last example, the number of vectors was the same as the dimension, and it was a basis. Here, the number of vectors is the same as the dimension, but it's not, right? So be careful. Don't just assume that because the number of vectors in your set is the same as the dimension of the vector space, don't assume that it's a basis, because it could not be. Right? And since these are dependent as well, that means you could write one of these as a linear combination of the other two. In fact, if I took negative 1/3 times V1, let me show you the dependence, negative 1/3 times vector 1 plus, and then another negative 1/3 times vector 2, I'm just seeing this here, equals vector 3. Right? You can see, you can write V3, you can write this guy very easily as a linear combination of these two. And then if you solve this equation for vector 1, you could see how vector 1 can be written as a linear combination of the other two. And if you solved it for vector 2, you could see how vector 2 could be written as a linear combination of vectors 1 and 3. Just know that they're dependent. They're not all needed, right, for this set. But they don't build P2 though, right? There are vectors in, it doesn't span, so there are vectors in P2 that are not linear combinations of these three. Right, so just again, be careful. Just because a set of vectors has the same number of vectors as the dimension of a vector space does not mean that it is a basis, but it could be, so you do have to check. Alright, and I've got one more here involving the polynomials, and then we'll get to some matrix examples. So here I have S's, my vector space this time is P4. Right, this is the set of all polynomials of degree 4 or less. I got vector 1, 2, 3, and 4. Right, these are all polynomials of degree 4 or less. I'll write that in again here. So I'll call this V1, V2, V3, the negative 5x to the fourth, and then V4 there. All right. The dimension. Now, again, if you didn't know the dimension of P4, you would have to check: does this set span P4 and is it independent? You'd have to do both. But since I know the dimension of P4 would be 5, right, based on our standard bases talk earlier, we can say immediately, without doing any work at all, that this set does not form a basis for P4, right? I can tell you right now that, since the number of vectors in S is less than the dimension of the vector space, right? You have 4 vectors in S, the dimension is 5. S will not span that vector space. Now they may be independent, but it doesn't matter. If they're independent, but the set doesn't span it, then it's not a basis. And again, you can go and figure it out, make a coefficient matrix and all that, put it in reduced echelon form, and you can see that yourself. But I'm going to jump to this, using these shortcuts when we know dimension. All right. Yeah, so since S does not span P4, S, this set of vectors, this set of polynomials, is not a basis for P4. Right? There are polynomials in P4 that cannot be written as a linear combination of those 4. Okay, great. All right. Moving on. All right, those were all examples involving those sets of polynomials. All right, now let's get to some matrix examples. All right. So here I've got an example where my vector space is that set of 2 by 2 matrices with real entries. Now, like I said many times already, if you didn't know the dimension of this space, then you'd have to check if these 4 vectors, and again there are 4 vectors here, right? There are my vectors this time are matrices, right? 2 by 2 matrices. So vector 1 is this 2 by 2 matrix with the 2, 0, 0, 3. Vector 2 is this 2 by 2 matrix. Vector 3 is this 2 by 2 matrix. Vector 4 is this 2 by 2 matrix. If I didn't know the dimension of this space, I would have to check, does this S span R 2 by 2? And is the set S independent, right? But I do know the dimension. All right, we know the dimension of the set of, remember it was m by n matrices I did, so a 2 by 2 matrix was just a product of rows and columns, right? The number of entries in each matrix. Okay. So the number of vectors is the same as the dimension. So that means S may or may not be a basis. You can't, again, don't just immediately jump to the conclusion that it has to be a basis because it has the same number of vectors as the dimension. You must check something. But the nice thing is you only need to check one or the other, right? Check the span. Does S span R 2 by 2? Or is S linearly independent? So I'm going to do that check for independence again because, again, it's a very similar setup to checking for spanning. So I'm going to take some scalar times vector 1 plus some scalar times vector 2 plus some scalar times vector 3 plus some scalar a4 times vector 4, v4. And when is that equal to the 0 matrix? The 0 vector, but in this case the 0 vector would be the 0 matrix, right? A matrix with all zeros. So let's see what this looks like. I'd have some scalar a1 times the vector 1 is this 2, 0, 0, 3 guy, right? Plus then a2 times 1, 4, 0, 1 plus a3 times the 2 by 2 matrix 0, 1, 3, 2 plus a4 times the 0, 1, 2, 0. And when is that equal to the 0 vector? And again, the 0 vector in this 2 by 2 matrix vector space is the 0 matrix, right, with 4 zeros. Now, again, nothing was mentioned about how vector addition or scalar multiplication are defined, so we're going to assume the standard operations, the way you normally add matrices and multiply them by scalars. So remember, in order for a matrix to, this side here would give me one matrix if I add them all together, right? 1, 2, but in order for one matrix to be equal to the other another matrix, the corresponding elements, corresponding entries have to be the same. So again, this leads me to a system of linear equations that needs to be satisfied, involving my unknowns, involving these scalars a1 through a4. So hopefully you're seeing now that it doesn't matter what the vectors look like. If the vectors are polynomials, if the vectors are matrices, or something from Euclidean space. When you're setting up these equations to determine, if S spans a vector space or if S is linearly independent, you're gonna end up with a system of linear equations. So the system that would need to be solved in order for to satisfy this, look at the first row, first entries. I'd have 2a1 plus 1a2 plus 0a3 plus 0a4 would have to be equal to 0. Right, the first row, first column entry of the 0 vector. So that would have to be true. Now let's look at the first row, second column entries. You have 0a1 plus 4a2, right? So 4a2 plus 1a3, and then plus 1a4 would also have to be equal to 0, right? The first row, second column entry of the other side, the 0 matrix. Now let's look at the second row, first column entries. You'd have 0a1 plus 0a2 plus 3a3 plus 2a4 would have to be equal to 0. And then lastly, look at the second row, second column entries. 3a1 plus 1a2 plus 2a3 and then plus 0a4 would have to be equal to 0. So I'm solving this system. All right. And again, I can set up a little coefficient matrix on one side, and imagine there's zeros on the other. And if you were checking for spanning, you'd have some just generic, maybe A, B, C, D over here, like a generic 2x2 matrix, representative of any vector in R2x2. You'd have like A, B, C, D, or V1, V2, V3, V4 over here. But either way, you'd have the same left side of the equal sign. You'd have the same coefficient matrix. So again, I'm going to put down here the coefficients of A1 down the first column, coefficients of A2 down the second column, coefficients of A3 down the third column, coefficients of A4 down the fourth column. And again, I don't really care what's on the other side, because again, I know I said I like checking for independence, but really I'm doing both. When I set up this coefficient matrix and put it in reduced row echelon form, I'm checking if S spans the vector space, right? If it ends up having a row of all zeros, I know it doesn't span. And I'm also checking for independence. If I put this coefficient matrix in reduced row echelon form, if every column is a pivot column, has one of those leading ones, then it's independent. And if not every column has a pivot, then it's dependent. Right? So I know I have I know I'm checking for independence, but really I'm checking for both. And then imagine there's zeros, or maybe even again A, B, C, D over here. It doesn't matter. I put this into reduced echelon form or reduced row echelon form again. And for the future too, for my future examples in this video. Remember how before with the polynomials, remember how the first column had the coefficients of the first vector, right, was related to the first vector. The second column of the coefficient matrix in the system was related to the second vector. The third column was related to the third vector in the set. The fourth column was related to the fourth vector, and so on. just like with Euclidean space. Each column of the coefficient matrix was a vector from the set S. Look at these entries. 2, 0, 0, 3. Look at the first vector. 2, 0, 0, 3. And that's the order I put the equations in. Remember that for the equations I looked at the first row first column entries, then the first row second column entries, then the second row first column entries, then the second row second column entries. If you look at these matrices in that order, boom, 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 that's the order these coefficients are coming in when I go from top to bottom on my coefficient matrix. So you see 2, 0, 0, 3, 2, 0, 0, 3, 1, 4, 0, 1, 1, 4, 0, 1, 0, 1, 3, 2, 0, 1, 3, 2, 0, 1, 2, 0, 0, 1, 2, 0. So that'll speed things up when I write my next example out and set up this coefficient matrix for a system I'd have to be solving to check if S spans the vector space or if S is independent. Alright, so now I got this 4x4 again. Let's go back here, make another matrix. Same, I'm going to just do A again. Matrix A, it's another 4x4. We have 2, 1, 0, 0, 0, 4, 1, 1, 0, 0, 3, 2, and 3, 1, 2, 0. Okay, get out of there. The last thing I entered was reduced to echelon form. Do it again. Look at that, the identity matrix. 4x4 identity matrix. So again, if you were doing the whole test for independence, like this would say that the A1 was 0, A2 is 0, A3 is 0, A4 is 0. Tells me that the only solution, right, the only solution to this is the trivial solution. So these are independent. And again, another way to think about that is look at every column. Every column has one of these leading ones in it. Every column is a pivot column, right? Every column is a pivot column. So we have S is independent. Fantastic. And because we know the dimension and the set S has the same number of vectors as the dimension, we can say now that S must be a basis. But remember the other thing you could also just check for both by looking at this. You look at there's no, all the rows are non-zero. All rows are non-zero. Right, there's not a row made up entirely of zeros, so we can also say that S spans, what was it, R2 by 2. Right. So we got both. If you want to look at this, the coefficient matrix, when you set up this system, whether you're checking for spanning or independence, you get the same coefficient matrix, set up the system, put it in reduced row echelon form, and these are the things you're looking out for, right, to see if one set spans the vector, if the set spans the vector space, or if the set is independent. So indeed, this set of vectors, these four matrices, form a basis. So S is a basis for that set of 2 by 2 matrices. Right, so these are like the building blocks, right? These are the building blocks, or just one example. Again, we saw earlier another basis, the standard basis. Those are simpler building blocks, but you could think of these as building blocks for R2 by 2, right? You can create any matrix in here by taking a linear combination of these, and all of these are necessary. You need every single one of them to be able to build every matrix in R2 by 2, right? They're independent. All right. The next example is again from R2 by 2. All right, so this time, I got 4 vectors again. Remember the dimension of this set of 2 by 2 matrices was 4. Okay, so again, don't just say, hey, 4 vectors, dimensions 4, it's got to be a basis. Not necessarily, right? You saw an example earlier where the number of vectors in the set was the same as the dimension, and it wasn't a basis, right? So you still have to check. So I'll check for independence like I like doing, right? A times v1 plus a2 times v2 plus a3 times v3 plus a4 times v4. When is that equal to the 0? The 0 vector here again would be the 2 by 2 0 matrix. All the entries are 0. Or you could set it equal to, right, to some, just take, this is any, a, b, c, d, right, where a, b, c, d are real numbers. I would use this. I would use this if I'm checking for independence. Can't spell. Independence. And I would use this, right? This is just some generic vector from R2 by 2. Right? This represents anything in there, and seeing if we can write it as a linear combination of these four. I would check this if I was use this if I was checking it for span. Right? Does this set span R2 by 2? But either way, do you see how I'm going to get the same stuff over on the left side? Right? I'll get that same coefficient matrix. And I'm just going to jump right to drawing that. And again, if I wrote the equations out, with the matrices and then set all the, and wrote that system, I would do it in the same order where I put the first row, first column entries in, did an equation for those, and then the first row, second column, an equation for those, and then second row, first column, an equation for those, and then second row, second column, an equation for those. So I'd have, down the first column when I write the augmented matrix, I'd have 1, 2, 3, 4. And again, that's all from the first vector for the first column. For the second one, 0, 3, negative 1, 5. These would be the coefficients of A2. And then for the coefficients of A3, from the third vector, 4, 1, 7, 0. And then for the coefficients of A4, from the fourth vector, 5, 3, 10, 4. And a bar, and then either a bunch of zeros over here if I'm checking for independence, or A, B, C, D, or V1, V2, V3, V4 if I wanted, if I was checking to see if it spanned. But either way, I'm putting this into reduced echelon form, reduced row echelon form. And again, back to the calculator. Right, you can do it by hand, right, using elementary row operations, Gauss short-on elimination. But again, I'm going to save some writing time here. So it's still a 4 by 4. Just entering all these entries. Bear with me here. Okay. Get out of here. Last thing I entered was reduced row echelon form, so I'll do it again. And look, there's a row of zeros. There's not every column is a pivot column. Alright, so again, row of zeros. If I put the A, B, C, D over on this side, there would be some scenarios where this, on the other side of the bar, where the other side of the equal sign wasn't a 0. There would be some values of A, B, and C, and D that would make a non-zero entry over here when I perform the row operations, and this system would have no solution. So there'd be some vectors that can't be written as a linear combination. Therefore, S does not span R2 by 2. Right, so there are some matrices. There are some 2 by 2 matrices out there that cannot be written as a linear combination of these four. Also, not all the columns are pivot columns, right? There's a column corresponding to the free variable. A4 would be a free variable, and the other three would be basic. But from there, I'm seeing that hey, this equation here would have infinitely many solutions. I could find solutions other than the trivial solution. because there's this free variable, right? So S is dependent. So strike on both of those. So for sure here, S is not a basis for R2 by 2. Right. And S is dependent. That also means that one of these vectors can be written, any of these vectors can be written as a linear combination of other vectors in the set. And I purposely made this one up. Maybe you saw it. See how vector v4, this 5, 3, 10, 4. See how that's just v1 plus v3. All right, if you take this matrix plus this matrix, you get that one. So I really don't need this one. I could reduce it down to a set of 3 vectors, so definitely not a basis, right? A set of 3 vectors is not going to be a basis for a vector space with dimension 4. It's too small. All right, and one last example, which is going to be a simple one, I promise you. Very short, using a little shortcut. So here I'm looking at the vector space of all, the set of all 2 by 3 matrices. So my vectors are 2 by 3 matrices. So I've got vectors 1, 2, 3, 4, 5, 6, 7. What was the dimension of our 2 by 3? Remember, the dimension of like the set of m by n matrices was m times n. This is 2 by 3. This is dimension 6. Saw this earlier. But there are 7 vectors in this set. And that's greater, right? The number of vectors in the set is greater than the dimension. So this set will be dependent. And you can set up the equation like I've been doing, set up that coefficient matrix corresponding to some system you come across, put it in reduced echelon form, and what you would see is that not every column would be a pivot column. There would have to be a free variable, and therefore more than just a trivial solution to that linear combination equal to the 0 vector equation. So S is dependent, meaning that S is not a basis for R 2 by 3. All right. Again, that's because there's one of these vectors should be able to be, any of these vectors should be able to be written as a linear combination of the others. Right. So there's one, at least one of these I don't need. Right, because it's too many. I need a set with 6 vectors to possibly be a basis for R2 by 3. Okay. All right, so that's a lot there. Right? And just remember what it means for a set to be a basis. Right? It's got to span the vector space and also be linearly independent. Right? You can think of a basis. You can think of a set that is a basis for a vector space as like the building blocks, for that vector space. Also, the dimension of a vector space is the number of vectors in a basis for that vector space. We saw some examples of some special vector spaces and their dimensions, right? The polynomials of degree n or less had dimension n plus 1. R m by n, the set of m by n matrices had dimension m times n. Euclidean space, Rn had dimension n. And if you know the dimension, you need to only show that a set is spanning or that it's linearly independent to show that it's a basis, right? And if you don't know the dimension, you have to show both, right? Which again, really just you could show both pretty quickly anyway, right? Remember, no matter how you cut it, no matter what the vectors look like, whether they be matrices or polynomials or Euclidean vectors, when you try to check for independence or check for does this set span the vector space, you're setting up a system of equations eventually, and in both of those cases you'll have the same coefficient matrix. You put that coefficient matrix in reduced row echelon form and check for rows of zeros to see if it spans or not. Check for does every column have a pivot to see if it's independent or not. It's simple as that when you boil it down. Alright, so I hope you guys have fun practicing this stuff, and thank you very much for watching.